Welcome to the SESRESAP Getting Started video tutorial. RESAP is the module used for inverting field measurements into realistic soil models. This is the basis for accurate grounding and interference studies. Indeed, correctly interpreted soil structures are essential to analyze grounding systems, conduct cathodic protection studies, examine electromagnetic induction problems, and compute line parameters. Given the field data, RESAP compares it to the apparent resistivities produced by different soil models and automatically converges to a soil structure which yields a closely matching surface response. In this tutorial, we will address the basics of using RESAP. Namely, we will cover how to input the field measurements, set up computation options such as the choice of soil model and choice of optimization algorithm, how to launch the run and monitor its progress, and finally, how to obtain the results so that they can be examined. If you want to follow along, be aware that the sample file used for this tutorial can be found in the SES Software Documents folder, under the Examples, Tools, SESRESAP subfolder. Let's get started. First, launch the program SESRESAP from the Tools folder of the software distribution. The application starts on the Project Info section of the Backstage screen, where you can document the case you want to study with a module and a project description. On this screen, you should also make sure that the correct system of units is selected so that the data can be correctly interpreted. Once you are done, click OK to move on to the main application screen. To input the field data, start by specifying the method that was used to measure it. In this example, we select the Wenner array, which is the most popular choice for grounding study applications. Then, select the quantity that was actually recorded by the instrument, apparent resistance or apparent resistivity. It is critical to make the right choice here, or the data interpretation will be completely incorrect. Optionally, you can also specify the depth to which the electrodes were driven into the soil for greater accuracy. Type in the data in the table, specifying the inter-electrode spacing of each measurement and the corresponding apparent resistance or apparent resistivity. As the data is entered, a graph is automatically updated so that you can visualize the trends. Note that you can toggle data points to be included or excluded from the analysis. Once the field data is in, switch to the Computations panel to select Analysis options. First, select the type of structure you want to use for modeling the soil. In accordance with how most soil structures are formed, a horizontally layered structure will generally provide the best approximation for the vast majority of cases. Then, examining the number of inflections in the apparent resistivity curve, you can deduce how many layers will be needed for the soil model. You can specify estimates for the parameters of each layer. These will be used as starting values for the conversions process that occurs during data inversion. Here, it is easy to see from the graph that the top layer has a resistivity of 100 ohm meters and an approximate thickness of 1 meter. It is more difficult to estimate precise values for the deeper layers, but we can at least establish a trend of resistivity values, recalling that changes seen in the measurements curve tend to be attenuated compared to those exhibited by the actual soil layers. You can also lock any value that you do not wish the program to try to optimize. Finally, you can select which optimization algorithm should be used for the inversion and specify its controlling parameters. For example, you can be more demanding on the target accuracy and increase the number of iterations to make the program search longer for an optimal solution. All the necessary information being specified, you are now ready to click on the Compute button. You will be prompted to save your work and warned that previous files will be overwritten upon proceeding. The Computation Trace panel informs you of the progress of the run. Once done, you can invoke SES Results Viewer for advanced plotting and reporting options, but a default plot will have appeared already, which you can also reproduce by clicking on the Plot button. If satisfied with the fit obtained, you may proceed to importing the resulting soil structure in the program where you wish to pursue the analysis of the system under study, for example, in SESCAD. If the fit is not satisfying, you may want to try guiding the software to a different solution by improving the initial estimate or trying different algorithm options. In conclusion, we remind you of multiple resources for learning more about the CDEG software suite. You can access the help manual by pressing the F1 key or from the ribbon. Our how-to manuals are also a good reference for learning how to apply SES software to the design and study of a range of engineering projects and scenarios. SES also offers a variety of training options, including seminars that include demonstrations with the CDEG software and practical exercises to help you bring your skills to the next level. Thank you for watching.